this is a preliminary file that I created to be able to start the session. This file is in Dropbox. You don't have to worry about it too much. I'll show you. In our Dropbox, in Form 4, in Waves, so you can open this file if you want later. But this is the file here with Cambridge questions. All right. So that's the location of the file. Although I'm really going to be using, I'm starting the introduction to review Waves by looking at this file. All right. We really intend to do questions more than anything else in this session. So let's begin. In this file, what I did was I copied the Cambridge questions, and I also have the mark scheme associated with the question. But we're still going to be able to discuss the questions so that it will make sense. All right. So firstly, figure 5.1 shows a full-scale diagram representing a sound wave of frequency 5.1 kilohertz in air. They're asking us to mark the position of one compression. And pretty much everybody knows where the compression is. When a sound wave is produced, a sound wave is made up of regions of compression where the molecules are closer together. This is a region of compression where these lines indicating the molecules or particles are closer together. And the opposite of compression, in between two regions of compression, there's a region of low pressure called rarefaction. All right? So we understand those terms. Do you think I should write those terms down as we go along? I need feedback. Or you can follow it without writing it down. No comment. I'll just write it down. So we understand what it means by a region. Firstly, a sound wave. All right, so we're okay with that. So that's what I was describing in terms of the sound waves. It's made up of a region of compression and regions of rarefaction. We also know that the wavelength yeah, we're okay with that. So the program is in Microsoft Word. Good. So the first part is the final region of compression. Clearly, any of these through the regions of compression. And using the full scale diagram, they're saying to measure the wavelength of sound. And as I just indicated, to get the wavelength of sound, we need to get this distance, the distance from here to there. And we look at that. That is a wavelength between any two regions of compression. Similarly, it will be the distance between any two regions of rarefaction, like from here to there. So these two represent the wavelength of sound. Now, it was intended that this be measured. This was supposed to be a full scale diagram. This is not a full scale diagram. We've reduced the scale of the diagram. But once you found this distance, lambda, that's the distance from here to here, you will get its value right here. You put its value, so many cm. All right? And once you've gotten that value, to find the speed of the wave v, we know v is equal to f lambda. They did, in fact, give the frequency here as 5 kilohertz, so this will be 5,000. Multiplied by the wavelength, which you would have physically measured in the full scale diagram. I'm just going to write it as lambda. And once you do this, you will get the, you can get the speed of the wave, no problem. Next part, just clear the drawings. I'm going to clear all the drawings. If you want to take a screenshot, you can do so in 5, 4, 3, 2, 1. Now, the next part, a sound wave is a longitudinal wave. Describe how a longitudinal wave differs from a transverse wave. And we know that we spoke about this in class last year. The longitudinal wave is where the particles vibrate along the direction of propagation, while the transverse wave, the particle vibrates perpendicular to the direction of propagation of the wave. All right. All right, just for the people who came in late, this is a Cambridge paper that I created for this session. This paper is already uploaded in Dropbox for you. So if you go into the Dropbox folder and you go into the Form 4 Dropbox, which is what you can see alone, and you go into your wave, you will see this file. Right? This is the file. I didn't select, I don't remember what years, it's one of the more recent years, 2008 or 2012. All right? Somewhere in that period. So these are the Cambridge questions. That's where the same file is located. But right now we're using it. So, I mean, you can pull it down, it's not a problem. But the point is, you don't have to pull it down yet because I'm showing it. And you can always collect it later. All right, good. Next one. We okay with this part here, right? I anticipate the answer is here. A longitudinal wave. A vibration, the oscillation is in direction parallel to the wave energy, and the transverse wave is perpendicular. Don't worry about its polarization. That's something that is not required for your syllabus. All right. Clear wall drawing. Okay. We go on to the next question now. A large number of television sets in a shop are tuned to the same station. The signal travels to some of the sets via satellite. Explain why electromagnetic waves are used to transmit television signals. Why do we use electromagnetic waves to travel television, to transmit television signals? Well, first of all, if you have the Earth, here, outside the Earth, there's a vacuum of space. Outside the Earth is space. The atmosphere is a very thin layer around the Earth. These satellites that orbit, they in fact orbit above the atmosphere of the Earth. And the only way waves could reach them, the only way waves could reach and travel into space, the only way waves can reach and travel into the vacuum of space is the wave has to be electromagnetic. None of the sound wave or other types of waves could travel in space, because only electromagnetic wave has the ability to move through a vacuum. So the first part of the question, which is explain why only electromagnetic waves waves are used to transmit the television signals, because only electromagnetic waves can travel through vacuum. We know that as one of the properties of electromagnetic waves. State the region in the electromagnetic spectrum used to transmit the television signal. What part of the electromagnetic spectrum do we use waves to transmit? And that will be radio waves. In order to, for communication from one place to another, you don't use light waves because light can be absorbed and attenuated. You use radio waves. So that's the part of the electromagnetic spectrum that that these television signals are made up of. So just why satellites are sometimes used to transmit. So just why satellites are sometimes used to transmit television signals. Well, a good reason for that is if you wanted to get a television signal from, let's say, this point on the Earth, right here, let's say that's Trinidad, and you want to get a television signal to, let's say, Canada, which is more like somewhere up here, right? You want to get a television signal from Trinidad to Canada. There is no line of sight. The curvature of the Earth will be in your way. So if you try to transmit a signal from Trinidad to Canada, you would not be able to, you would be using, first of all, a satellite, a dish, all right? Not that high, but you'll be using a dish in Trinidad and you'll be pointing it and trying to line it up with a dish in Canada. Because of this part of the Earth will be in the way, the signal would not be able to reach Canada. So if you, because of the curvature of the Earth, to get signals from one point to another, satellites are used to beam the signal up and then the signal can be beamed down to the other location. So the curvature of the Earth does not get in the way. All right? So just why satellites are sometimes used to transmit television signals. The main answer to that is so that the curvature of the Earth does not get in the way of the line of sight. Right, so the curvature of the Earth does not interrupt the line of sight. Right? That's why we'll use a satellite. Again, as I just illustrated, the curvature of the Earth from Trinidad to Canada, the curvature of the Earth will get in the way. Well, I mean, you can make it worse. You can think of Trinidad sending it to somewhere in Greenland. All right? There's no line. It's more obvious now. There's no line from here, no straight line from here to Greenland because the Earth itself will get in the way. So you have to send it to a satellite who will then beam it across. That's clear. Get back to the question so you understand that. All right. In this question, can you read this part? Can you read this part quickly? So hopefully you've read that and I can now answer it. Well, back to the Earth scenario. Just clear this and draw it over because getting kind of messed up. Again, we have the Earth. It's a little bit bigger. And we have two locations on the Earth. We have one location here, let's say. And we have another location where you want to get the signal to. In fact, right here, very close to each other. So from the question, yeah. So it's a ground-based transmitter near shop, right? So this one, you're getting the signal directly. The first person is ground-based transmitter very near to the shop. The signal is coming directly from here to here. Ground-based transmitter, okay? And the second one is going up to the satellite. The second transmission is going up to the satellite that is up here. So the signal is going up all the way to the satellite, and then it's bouncing back down to here. So you have two signals, two televisions. One television using the satellite signal, and one television using the direct earthbound system. So clearly, if you think of speed, because these satellites are several hundred kilometers off, not a short distance. That distance is, a couple kilometers, not a couple kilometers, but 150 kilometers, let's say. While this distance would be a shorter distance. So the wave, the signal must travel all the way up to the satellite and then travel back down to the Earth to be able to pick up by the other television, while one television is showing the signal live. And the person who is observing the two televisions sets the question, says they're observing a time difference of 0.24 seconds. All right? They want you to calculate the distance traveled by the television signal in 0.24 seconds. Now, what we know about electromagnetic waves is that they all travel at the same speed. All electromagnetic waves travel at the speed of 3 by 10 to the 8 meter per second. That's how fast they travel. And if you're talking about a time of travel of 0.24 seconds, they're asking how far would it travel in 0.24 seconds? Now we know distance is equal to what? Distance is equal to speed by time. So it's a simple matter of multiplying these two, 0.24 by 3 by 10 to the 8. And that will give you how far the return journey that is. It will give you the return journey of this signal going up and coming back down. So that's 2 marks. All right. Again, this is the answer to the question. I just went through the answer here with you, but there's a written value, the same calculation, everything I'm doing here is already written here for you. But I'm just trying to be able to talk you through it. This other question is something that most of you would not be able to do. Remember, I showed you a video that we did in school of waves. This is something might be a bit beyond what you're doing right now, which is very few of you would have already been able to see a cathode ray oscilloscope, right? So I'll leave this question for you to look at. The answers, again, they're right here. And I want to look at this question here. Figure 4.1 represents a microwave traveling in air. And they're giving you the distance between A and B, it's a microwave, right? And they're telling us the distance A to B is 40 centimeters. And they're asking us, state the speed of the microwaves. Again, because the microwave is part of the electromagnetic spectrum, the speed of the microwave would be 3 by 10 to the 8, right here, 3 by 10 to the 8. determine the wavelength. In this case, we want to find the wavelength of the microwave. In order to get that, we know the distance from here to here is 40 centimeters. From here to here is lambda. That's 1 lambda. From here to here is another lambda. But from here to here is a half lambda. So that 40 centimeters is really equal to 2.5 lambda, 2.5 lambda wavelength. Again, that's 1 lambda, that's 2 lambda, and from here to here is a half lambda. So from here, we can get that lambda is equal to 40 cm over 2.5. The calculation suggests that that is 0.16 meter or 16 centimeter. Easy. Describe how microwaves are used in the transmission of television signal by satellite. And here there's a whole host of reasons. I already highlight why we use microwaves to transmit television signal, because it has to go through the vacuum of space. Only microwaves could travel. Electromagnetic waves could travel through space. But there are several other. The first one is that. The second one is when the microwaves are traveling up around the Earth, you have a region called the ionosphere. Normally, waves hit the ionosphere and they don't penetrate, they're actually reflected off the ionosphere. Microwaves, on the other hand, is able to penetrate the ionosphere to reach the satellite, and then it can be reflected back down. So this is something, another reason. All right. Okay, so that takes care of these questions that I wanted to do as introductory questions. The second part of this is I want to go through a couple of the properties of waves. One of the things we did with waves is we spoke about reflection of waves. And, sorry, I'm gonna clear. We spoke about reflection of waves. So if I have a surface like this, and I have a wave traveling to that surface like that, this is the position of the wave now. This is a reflecting surface. Normally with a reflecting surface, we will have a few lines behind it to indicate what it is in fact a mirror. So we have a mirror there. Now, so this is a wavefront, as we know, and that wavefront is traveling in some direction like so. Now, the direction of travel of the wavefront is called the ray. It's called a ray. And this ray is in fact traveling in a very specific direction. What is the relationship between the ray and the wavefront? Again, that's something we already met. The ray is always perpendicular. The ray is always perpendicular to the wavefront. So I don't really have a protractor, but I can make one. By creating a square. I need to put this in another layer so I don't. Right, okay, I got it. that's nice. I want to make it a little bit see-through. And I also want to change the color of it a little bit. Right. So I'm going to use this as my protractor. So I'm going to bring it up here. I'm going to rotate it. Like so. So all of a sudden, this is my protractor. Now, if I want to know the direction of travel, let's see, go back to the wavefront. So I have my wavefront here. And let's say this edge of the wavefront is, this point on the wavefront is moving towards the wall. What direction is this moving? What is the direction of motion? I just said that the ray is always perpendicular to the wavefront. So be able to find where this point, and I'll give this point a name, I'll call it the point X. So if the point X is part of this wavefront and the entire wavefront is moving up like this, I mean, this wavefront, as I said, will eventually move from here to there, okay? And then it will continue to progress forward, 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 like that. That's how it's going to travel over time. All right, that's how it's going to travel over time. But I don't want to get into that. The question is, in fact, I'll leave that there. The question is, what is the direction of movement of this point X? And we said the direction is perpendicular to the wavefront. So to put the direction of motion, to put the ray in this situation, I can draw a line like so. And this is the ray. I just have to make sure that it is along the edge of the protractor, as I call it. And that's how the ray is traveling. This is how the ray is traveling along that path. Okay? Again, why is that? Because the ray is always perpendicular to wavefront. Any point along here, any one of these other points along this wavefront will similarly be traveling along a similar path. So I could see I'm looking at this other point, this other end here. How is it traveling? It's traveling along that path. Right? Each one of these points traveling along that path. So this is where the wavefront is now. This is where it's going to be later. Now, what do we know about this ray is when this path, when it hits here, it's going to reflect according to the law of reflection. So to be able to show how it's going to reflect, we first need to draw a normal, which is that. And a normal is normally a dashed line. So that's our normal there. That's our normal there. It's going a little bit tighter. So we see our incident ray, we see our normal. Guess where our reflected ray is going to be? Our reflected ray is simply going to be like this. So that the angle of incidence is exactly equal to the angle of reflection. You get that so far? All right? So this is how our wave is reflected. All right? The wave is here, the wavefront is here. These particles are moving in this direction, or the energy is moving in this direction, and these are successive wavefronts. Now, I'm going to clear some of these. So we know this wavefront is going to be along a series of paths. And when this wavefront reaches the wall and hits the wall, the wavefront is going to be reflected, and the reflected wavefront is going to be perpendicular to the reflected ray. This is our reflected wavefront here. This is the one that is going in the opposite direction. All right? But remember, we had done something in class. We've spoken about what it looks like while it is being reflected. And I said to be able to figure out what it looks like while it is being reflected, let's say the middle of it reaches the wall. What it looks like while it's being reflected is you draw this one here as if it was not interfering, or the wall wasn't interfering with it. And this part of it here, this part wouldn't be there. This part will simply be reflected along like this, about the wall like that. And this would be the wavefront while it is being reflected. This is before. This is while it is being reflected. This is after it has been reflected. We clear on that? Everybody clear that? Before, after, and this is while it is being reflected. It looks like a V. This part of it is still moving towards the wall, so it looks just like this, and this part of it has been reflected, so this part will be perpendicular to this. It will be perpendicular to this ray. This part is still perpendicular to the incident ray. The reflected part is perpendicular to the reflected ray. So that's how we get to see what the wavefront looks like while it is being reflected. All right. So that's the first property of waves that we spoke about, which was reflection. I'm going to clear this now. So we've covered reflection. We've seen videos of this on, I was supposed to put the videos in YouTube, in Dropbox for you all, but I just never got a chance. What I want to do now is ask if there's any wave questions that you all had trouble with that you want me to talk about specifically. I will go into them now. Any waves question you tried and you had trouble? This is the worksheet that I'd given you, right? But any waves question you tried and you had trouble with? This one only goes up to what? 2000. Doesn't matter. Anybody hear me?
Yeah.
All right, I heard one response.
Good night.
Good night.
Yeah, I'm hearing you.
Awesome. All right. So, is there any wave question you all tried that that you had trouble with, that you want me to work? You could text. You can write it in a chat window. That's a no. All right. So I'm going to continue with a few of these questions, right? Just to give you a range of introductions. I'm not teaching, I'm answering questions. In fact, I'm teaching through answering questions. So let's hope that works. Let's go from the top. Explain what is meant by each of the following terms. What is a progressive wave? Anybody would like to venture an answer? So what is a progressive wave? You can type it to the text window or you can utter it.
A progressive wave is a wave that spreads from one point.
Yes, a progressive wave is a wave that travels from one point to surrounding areas, so it's spreading. Now, everybody knows what a pulse. I went into detail what a pulse is. All right. A pulse is a short duration wave. All right. We know what a longitudinal wave is. A wave in which the medium vibrates parallel to the direction of motion of the energy. And we know what a transverse wave is. So let's get into this. You all could see this, or you'll make it bigger.
Make it a little bigger.
Right. So let's awesome. Now, some ships employ sound waves in determining the depth of water below them. So this ship is going to determine the depth of the water below them. These sound waves have frequency above the range of human air. And when we say above the range of the human air, we know that the human air is theoretically able to detect sound from 20 to 20,000 hertz. Remember this. So therefore, this wave must have a frequency of more than 20,000 hertz, and it's called ultrasonic. A short pulse of such sound is emitted by a transmitter. right there. It travels to the ocean floor and it's echoed back or reflected back to the receiver close to the transmitter. So right here you have a transmitter and a receiver. So you're sending one wave and you're listening for the reflection. The depth of the ocean can be determined from the time lapses between the transmission and reception pulse. We know this topic. We've spoken about this already. We know that the equation is V is equal to 2 times the depth over the time between sending the pulse and picking up the echo. That's the equation I've done with you, that V is equal to 2D over T. Right. What difficulty would be encountered if the transmitter were to send a continuous sound wave? What difficulty would be would occur if the transmitter, instead of making a sound and then have this sound work its way down, and then you're silent until you hear the sound, what will happen if this transmitter was continuously sending waves? Now, that's kind of obvious, because if the transmitter was continuously sending waves, remember the question says that the transmitter will where is it? Yeah, it is the receiver is close to the transmitter. Now, if the receiver is close to the transmitter, if you continue to transmit sound, wouldn't the receiver pick up all of those transmissions? Yes, it would. So you would not be able to detect the sound that was reflected off the ocean floor and differentiate it from this continuous sound that is being created by the transmitter. All right. So what difficulty would be encountered if the transmitter would send a continuous wave? The detector would not be able to differentiate reflected sound from transmitted sound. I'll write that somewhere. The detector would not be able to differentiate between reflected sound, the sound that came up from the ocean floor, as compared with the sound that was being produced. Think of it as you standing up, let's just go to this other program. If you have a wall and you standing here and you send out a sound, if you send out a sound and you stay quiet, then you'll be able to hear the reflected sound. We understand that. But if you send out a sound and you continue to scream, instead of making a sound, you continue to scream, you would not be able to know when this echo returns, because the sound that you're continuously making would be able to override your air, and your air wouldn't know when this echo comes back. That's basically what we're saying. So in this question, you have the ship producing sound, and the reflected sound is being picked up. And if the ship continued to produce sound or ultrasound wave, it would not be able to pick up the reflected sound, because this produced sound will be so much more intense and it will mix with, all right? So that's the 3 marks. The detector would not be able to differentiate reflected sound from transmitted sound, and therefore, of course, you wouldn't know the time delay and all of that. Why is it necessary for the transmitter to use pulses of sound? So that, again, following up the same idea, why is a pulse used? A pulse is used so that you can know when the sound is produced and you can know how long it takes to return. So you have a silence region. So these 2 answers kind of tie together. So you scream and you shut up and you wait for the sound to hit and you come back, and then you'll be able to time to work out what time it takes for the sound to travel from you to the wall and back. Next part. The ultrasonic transmitter has a frequency of 40 kilohertz and a wave velocity. What is the wavelength? Again, V is equal to what? We know V is equal to F lambda. And we can get lambda is equal to V lambda would be equal to V over F. And in this context, it will be 1500 over 40,000. 40,000. Why 40,000? Because you have a kilohertz. Kilo means 1,000. Next part. The time taken for the echo to return is 200 milliseconds. Calculate the depth. That's it right there. So you know V is 1500. 1500 is equal to 2 times the depth over the time it takes for the sound to return, which is 200 milliseconds. So 200 milliseconds is really 0.2 seconds. That's what 200 milliseconds is, 0.2 seconds. So you just have to crunch the numbers and you get the depth. That's easy enough to work out. This 150 meters. Let's see. Did the long way. 1500 multiplied by 0.2 divided by 2, right? 150 meters. Okay, we understand that. I'm going to clear. All right, I'm going to look at another one now. I'm trying to get different types of questions. Is there any of these questions we have not yet worked? You all have the handout. Is there any of these questions we've not worked? Oh, nobody talking to me.
So you can scroll up a little bit, please.
Scroll up.
Yeah.
Let me just make it a little bit smaller.
Oh.
It's kind of taking over my whole screen.
Oh. I saw a
Scroll up.
question. No.
Sorry?
I saw a question just now and it looked unfamiliar. But
Okay, I'm gonna scroll back now. Scroll up.
I'll look in for it, but I don't see
You have the
it.
handout. You have this handout. Everybody have this handout.
Yeah.
So if you
I'll
pull
look
up your
for it
handout.
and then I'll tell you back.
Sure, sure. Anybody else? We have 15 minutes again for the session. June, okay, somebody's asking, Ryan is asking June 2007, paper 3. Okay, I can go to that. 2007 is this way. 2007, paper 3. Okay, let's go through this.
So I know we did this one in class already, but I just don't understand the last part of the question.
Sure, I'll do the last part then, which is part C. This part here, right? Part C, yeah?
Yeah.
Okay. The diagram below shows two loudspeakers, L1 and L2, connected to the same source of vibrating in phase with each other. Good. The loudspeaker produces notes of frequency 132. All right, here I'm going to clip this out of here. because I can't be scrolling up and down all the time. Oops, I need more. I'm going to put it in a new Word file. Right, so I can see it. Let me just get rid of some of these pieces. Right, so I have all of it in one place. Right. The loudspeaker produces notes of frequency 132 hertz and the speed of sound. What's the wavelength? Again, wavelength lambda is equal to V over F. And they gave you the speed of sound to be 330 and the frequency is 132. Oops, 132. Undo. 132. So we got an answer for that, no problem. Next part. Consider at any instant a sound wave starting at L1 and proceeding in the direction of A. A is the middle here. Sketch the graph of the displacement of the air molecules against positions for the first 7.5. Right, so we needed to work that. We would need to work that wavelength, which is 330. I think we got this to be 2.5, as I recall. 132, which is that 2.5. So this wavelength is 2.5. No problem, that's a meter. And then consider at an instant the sound starting at L1 and proceeding in the direction of A. Sketch a graph of displacement against position. You have to sketch a graph of displacement against position for the first 7.5 meter. Now, if the wavelength, they want us to do for 7.5 meter and the wavelength is 2.5, so it's 7.5 meter, how many wavelengths do we have? Exactly 3. This is 2.5, oops, sorry, undo. This is 2.5 here, right? That's one wavelength, that's 2.5. This will be a second 2.5. And to get to 7.5, that's from here to here, now 5 meters. To get to 7.5, you have to do one more. Right? So this is the graph they want us to sketch. Again, sketch a graph of displacement against position for the first 7.5 meters, given that the wavelength is 2.5. So this is 7.5. Again, this is displacement against position. We good. A student walks along the line XY. A student is walking along this line XY. At both A and B, the sound is loud. At both A and B, the sound is loud, whereas C, the sound is quite faint. Explain these observations. And again, why is the sound loud here? Again, because of constructive interference. Okay? And why is it loud here? Again, because of constructive interference. And why is it soft to C? Because of destructive interference. All right? Explain these observations. Sorry. And I'm going to say at A and C. I'm going to do this in a different color so that we can differentiate between it. Yeah? At A and C. rubbish, at A and B, not C. At A and B due to constructive interference. And at C, it's due to destructive interference. You okay with that, right? And what is constructive? You can expand on that. A constructive interference is where two, in this case, it's sound. So two regions of compressions meet, and two, regions of rarefaction meet. So that's constructive. Destructive will be when a region of compression meets a region of rarefaction. Next part. We got this. I can clear this drawing in 3, 2, 1. Clear all drawing. Next part. With the frequency of the notes still at 132, the loudspeakers are moved closer together. And we had spoken about this equation. The equation is lambda undo. The equation the way I presented to is y is equal to lambda d over a. Lambda d over a. Now a is the separation. A is the separation between these loudspeakers. D is this distance. And y is the distance between the two regions of constructive interference. So that's y, and of course lambda is the wavelength of sound that we're using. Now, with the frequency constant, once the frequency is kept constant, the loudspeakers, the frequency being constant means lambda is also constant. With the frequency still at 132 Hertz, the loudspeakers are moved closer together. Moved closer together means what? A is decreasing. They move closer together. A is decreasing. What will be the effect on the observations of A, B, and C? The observations of A, B, and C is to determine y. Y is the distance between A and B. So if A is getting smaller in the equation, A is decreasing, what happens to y? So let me give you an example. Let's say y1 is equal to 5 multiplied by 10 over 2. Y1 would be 25. 5 by 10 is 50, 50 over 2. But what would happen, y2? What would happen if we keep lambda and d constant? And we're going to use easy numbers. Suppose I increased the denominator from 2. Suppose I decrease, A from 2 to 1. What's going to happen to y? See that? So when A decreases, what happens to y? Y increases. And that's the answer to the question. What effect would the observations have on A, B, and C? We would find that the distance A to B is now larger. Because the denominator A is getting smaller. Right? I'm going to clear that in 5, 4, 3, 2, 1. Next part. The frequency of sound is now changed to 264. What happens to the frequency? We know that that V is equal to F lambda. We know, and I keep telling you that this is constant. This is fixed. The speed of sound in a medium is fixed. The speed of sound in a medium doesn't change. So whenever you increase the frequency, what must happen? What happens to the wavelength to keep the product the same? The wavelength must decrease. Whenever the frequency of sound increases, its wavelength decreases. Right? Whenever the frequency of sound increases, the wavelength decreases proportionately. And that is so that the product is a constant. So back to the question. The frequency of sound is now changed to 264. So when the loudspeakers return to the original position, will the wavelength now be larger or smaller? We are seeing that the wavelength would be smaller. The wavelength would be smaller, not larger. And what effect will this have on the observations of A, B, and C? What effect would this have now on the separation of A, B, and C? And again, we go back to the same idea that Y is equal to lambda D on A. And here we are clearly seeing that lambda is getting smaller. Lambda is getting smaller, it means this is decreasing. And if this is decreasing, guess what's going to happen to Y? Y is going to decrease. Right? So this last part, to find what will happen between A, B, and C. A, B, and C will get closer together. Right? They get closer together. And this one, they got further apart. And this one, they're getting closer together. All right. To be clear on that. I'm going to clear the drawing now. Everybody understand that? Ryan? Ryan?
Yeah.
Is there anything there that you want me to clear still?
No, I'm good now.
You sure?
Yeah.
All right. This entire video I'm going to put up in YouTube as soon as I'm finished with the session, and I will email a link to everybody. So if you want to consult and look at it again to get clarity, that can happen. All right. Now see, Khadija has a question, and Alicia has a question, and Kevin has a question. All right. What I want you all to do is to request. I want to end the session now. I said 10 o'clock, and we're gonna stick to time. But I will continue working on these questions. Just send me an email with these 3 requests for solutions. And tonight I will sit down and try to write up the solution to these 3 questions, and I will broadcast it to the entire class. All right, but I want to keep the time as we had established it. We started at 9 and now it's 10:01. So I'll end the session now, and I'll then go and encrypt this file, organize this file to upload it to YouTube, and I'll send you an email with the link to the file. Stop recording.